So, today's a big day for us. And usually when you have big days, we're going to learn a major concept. That's what's happening today. We're going to learn a major concept. We really have 2 more big days left. One's going to be today and one will be next week. As you've probably noticed, I tend to teach things and just to let them sit there. And the next day I teach something else. And then like third day or block day, I try and wrap it all up together. That's kind of my teaching pattern. That's the method I use. Today I'm going to teach a few things and try and wrap them all up in one at the end of the day. Do you guys know what a Megazord is? Anybody? I didn't think so.
Oh, I've seen that.
Oh, yeah.
Is
that
Power Rangers.
Oh, yeah.
You know the.
That show after.
I'm going to try and point. The what is that? That's the Triceratops and the no, that's the saber-toothed tiger. That's the Triceratops. This is mostly T-Rex up here. They all come together and they form this one big powerful monster.
Oh, yeah.
Really, it's a machine. And that's what we're going to do today with some ideas. We're going to form a Megazord of an idea.
Okay.
We're going to start with ratings and degrees, and this will be review. Should be review.
So should we write this down so we have it still?
Yeah, and do what you always do. Do what you do anyways. This would be 0 degrees. Oops.
Oh, that's so cool.
Off to a good start.
Wow, that's awesome.
We being
0 degrees or 0 radians.
0.
If I go completely around the circle, if I trace all the way around the circle, it's 360 degrees. And how many radians is that?
6.2.
Give me a pi in there.
2 pi, yeah.
Good.
Yep.
2 pi radians.
That one.
I knew it was 6.2.
So if I go halfway around the circle, that'd be 180 degrees. How many radians would that be?
1 pi.
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 Yep. Half of 2 pi, so it's just 1 pi radians. Here's my 90 degrees. How many radians is that? Half a pi. We'll call it pi over 2. And you don't have to put the word radians if pi is in there. If you see a pi, you know you're talking about circles, you assume it's radians. If you have like a decimal, like 1.8 or something, then you have to put radians at the end. What's this point in degrees and radians? Either one. 270 degrees.
Yeah.
How about the radians? 3 over 2 pi. How'd you get that?
I don't know.
I call it 3 pi over 2. Here's how I do it. I just think if that's 1 pi over 2, then that's 2 pi's over 2's, and that's 3 pi's over 2's. You're just counting pi's over 2's from 90 degrees. Those are called quadrantal or quadrantal angles. Quadrantal, I don't really know. But all the right angles are called quadrantal. They're right angles on the circle. We can also find some other important, useful ones. If I draw this angle right here, and that's 30 degrees, we'll say. I want that to look like 30 degrees. 30, 45, oh, that's not what I want to do. 30, 45, and 60 are the very important angles we're going to have within those quadrantal angles. And the nice thing about a circle is you can always think of everything as being up here in the first quadrant, somewhere in this range. If I had an angle over here, let's say that's 150 degrees. This whole space is 150 degrees, but this little angle right in here is basically the same as this angle here. So if you have an angle that's 150 degrees, you can treat it like it's a 30-degree angle. Because you're basically finding this angle from this quadrantal or this quadrantal. These are called reference angles. A reference angle is how you take angles that aren't in quadrant 1 and treat them like they're in quadrant 1. Make that a little bigger. We'll talk about that for a while. This right here, I'm going to call 100 from this point here. It's 125 degrees. What would its reference angle be? What's the corresponding angle in the first quadrant? I'm sorry, 225. Thank you. 225 degrees. What would its reference angle be in the first quadrant?
45.
45. Because from the 180, we go 45 further. So it's basically like having a 45 degree angle. Okay, so a reference angle takes whatever you have and puts it with its corresponding angle in the first quadrant. Vertical only. Writing at this point. We'll go here. This would be 90, 180, 270, 330. Where would its reference angle be? 30. It's always basically going to come down to a 30, 60, or 45. Okay, and you're just finding these angles from the quadrantal ones. Those are the easy ones. We like them because they're easy. 90 degrees and 45 degrees. One more. Say I took it and I made it I'd like to do it in radians, but I'm not sure if we're at the point yet we can handle that. If this is pi over 2 radians up here, pi over 2 radians, and this is halfway further, what would this angle be in radians? I want this angle right here. What would that angle be in radians? Ian, what are you saying, Billy?
3/4? I don't know what.
Okay. 3/4 pi. How'd you get that?
Because it's just one pi right there. It's the half of one that.
Good. This would be 1/4 pi, because this is a half pi. So this is 0 pi, quarter pi, half pi, 3/4 pi. This is 3/4 pi radians. This whole angle here. And its reference angle in the first quadrant would just be pi over 4, or 1/4 pi radians. So part of the reason people think radians is hard is because we're not familiar with it. It has these pi's. But the main reason people don't like it is you use a lot of fractions. You have to use halves and quarters and thirds, and even sixths quite a bit. So think about it like you're counting pieces. If this is half a radian, or half pi radian, sorry, pi over 2 radians, this would be pi over 4. And there's 1, 2, 3 pi over 4 radians. Okay, is there a question about that at all? That was reference angles. That was idea number 1 of our Megazord today. From the center of a graph, the coordinate plane, I travel right 5 units from here to here, and up 3 units from here to here. Where would this point be? People, come on. Where's this point right here? 5, 3. Thank you.
Yeah, the probability.
Sorry, all I heard was the 3. Okay, that's it.
Okay.
Got it. Thank you. It's clear at the point 5,3, and the point I'm trying to make is an x-coordinate at the point 5,3. An x-coordinate is telling you distance from the y-axis, and a y-coordinate is telling you distance from the x-axis. This has a space of 5 going left to right. This has a space of 3 going up and down. From here, I could find all my 6 trig functions of this angle. If I call this my theta, I could find 6 trig functions. I know that this is 5, and this is 3. This would be 25 plus 9 is 34. This would be the square root of 34 by doing the Pythagorean theorem. And then I could do sine, cosine, tangent, secant, cosecant, cotangent from there. Okay, is there a question about that at all? That should be pretty straightforward. Here's kind of the new idea. Instead of having 2 distances, suppose all I have is a side of length 3. I know this is length 3, and some angle theta, where you would know what theta was, but for now we'll just keep it theta. Can I still find this point right here? Anybody tell me how I could find that point, given only a side length, the hypotenuse length really, and an angle? Okay.
If you can find the distance between whatever, like 0, let's say,
Mm-hmm.
and x, well, whatever, between that, the perpendicular point.
So if we call this x and this y.
Yeah.
Okay, so this is distance x along the bottom, distance y across the top. How can we find y?
Sine,
Good. Keep going.
sine theta over y.
Well, we'll just start with this. You know, sine of theta is what? You know, it's the opposite over hypotenuse. So sine of theta is y over 3. So 3 sine theta, whatever that angle is, will give me my y coordinate. And in the same way, I know that cosine theta is going to be x over 3, which means that 3 cosine theta is going to give me x. If I do 3 cosine theta, I get my x point. I do 3 sine theta, I get my y point. That gives me my coordinate. So with just a side length and a theta, we can find anything, or find the coordinates that we need. Question there.
Could you find it if you had y and theta, like if you had like 3 was where the y is?
If you have any 2 things, you can find anything. If this is just trig, we've just taken our triangle and smacked it down on the coordinate plane.
Okay.
Always centered at 0, 0. So none of the trig is new. Yeah, it's just we can now think about x's and y's as coordinates, because the idea I'm trying to get at is coordinates are just distances. And that's what the triangle was, distances. Okay. The process of using an angle, using a theta here, well, since the angle can change, really this point could move anywhere up or down the circle, or in a circle. So we can think about finding any coordinate on any circle giving a certain hypotenuse. Right? In the last one we did it with a hypotenuse of 3. But to make things easy, instead of doing 3 sine theta, we just always pick a 1 for a hypotenuse.
Always?
Always. Because once you find a 1, I can multiply by 3 to get my 3 sine theta, or multiply by 5 to get the 5 sine theta. But if you have a 1, it makes everything much simpler. That 1 is our basic unit, which is why this is called the unit circle. Okay? This circle here is called the unit circle, and that's the big idea we're going to get to today. Start here. How can I find the x-coordinate of this blue point? if I want the x coordinate, I can think about this triangle, which is a right triangle, and I want this x distance, which is cosine. Cosine of theta would be x over 1, which really just means that the cosine of theta is x, because the hypotenuse was 1. That's what makes this easy. The hypotenuse is 1. The x coordinate is just cosine theta. Where's my next one? There it is. What's the y coordinate going to be?
Sine theta.
Sine theta. The y coordinate is just going to be sine theta.
Will it always be cosine x and sine y?
And that's the most important thing today. Cosine gives you an x coordinate. Sine gives you a y coordinate. And it's just because it's these triangles, cosine is adjacent over hypotenuse, and that gives you an x distance right here. So this process can be used to find any points. Okay? Any point is going to be some angle from the center and some hypotenuse distance. We like to think of the hypotenuse as just being 1 unit, so we can find everything from there. Okay. At this point, and actually at the last slide, I'll cover tonight's homework. Tonight's homework we're good. In fact, you won't even really see this on tonight's homework. We're going to teach it today so we can see it again on Monday and just kind of keep working with it.
So are they going to give us like what the angle measure is, or are they just going to give us their or whatever?
They'll give you anything and everything, and you got to take everything and make it anything.
So it's still going to be just cosine, but they give us
Mm-hmm.
equals x or whatever.
Mm-hmm. Yep. So there's cosines and sines. Okay, is there a question about this?
No.
Okay, here's our last third idea. This, we've talked about special right triangles before. We're going to do it one more time. In fact, we'll really do it lots more. This is a 45-45 triangle. These pictures are actually accurate. This is 30-60. And they have hypotenuses of 1. Each have hypotenuse of 1. We're going to solve these triangles. We're going to find the other missing sides. How do I find that side right there? Sure, we could do law of sines. We could do cosine 45. Those are going to give us decimals when we do it in our calculator. And I would like to avoid decimals for a little bit. If you think about this triangle, what do we know about this triangle? What's the term we would use to describe it? Isosceles. Good. What do we know about isosceles triangles? These are both the same length. The two angles are the same. That's how we knew it was isosceles. Yeah. So a squared plus b squared equals c squared is still my theorem I'm using. But since they have a same side length, so that should be a c squared. A squared plus b squared equals c squared. These are like terms. I can add them up. I want to solve for a. I know that c is 1. My hypotenuse is 1. So I can go back and change these c's to 1s. And I get a squared equal 1 over 2, which means that a equals the square root of 1 over 2, which becomes 1 over root 2, which becomes root 2 over 2. Both of these sides are length root 2 over 2, if the hypotenuse is a length of 1. Because really, 45, 45 right triangle. Let's see if this does what I want it to. It's really just a square. It's half a square, which is why these are isosceles from the right angle. Okay, let's talk about this one. It's actually a little bit harder to figure out if you're not going to sine cosine and you don't have your things memorized. Okay, we should have memorized that this side here is always half your hypotenuse. You should have that memorized. But I want to go through and kind of figure out why that's the way that it is. Do you know why a 30-60 is special? Do you know why we grabbed this first triangle because it's a square, it's half a square. What's special about this one? Yeah, but what's it half of? What's that triangle half of? Yes, it's also half of. It's half of an equilateral triangle. Right? This has a length of 1, and a length of 1, and a length of 1. These are all length 1. So that's how we know that if this is 1, since this whole side is length 1, this must be 1/2. So it's half of the whole. That's where that comes from. And now that we know that that whole side is 1/2, I can find this length again by doing the Pythagorean theorem. So I have down here a squared plus b squared equals c squared. Doesn't really matter which one's a or b, so I'm just going to say 1/2 squared plus b squared equals 1 squared, which means that a 1/4 plus b squared is 1. If I subtract a 1/4 from both sides, I get 3/4. It's b squared. I wrote this backwards, but it's okay. 3/4 is b squared. I square root both sides, and I get √3/2 equals b. So this is a side length of √3/2. That's why I wrote pi there. Subtract the 1/4 from 1.
The square root of 4 times the 3 squared.
That's a good question. So the top, when it's squared, becomes just √3.
Yeah.
The bottom, when it's squared,
Oh.
square root of 4 is 2. Yeah. Whoa. Bring all this up and kind of make it separate. So these two special right triangles, the 30, 60, 90 on the right and the 45, 45, 90 on the left, are super, super handy and super important. Really? Come on, just slide. Thank you. Get rid of this. Get rid of this. I'm going to slide this one closer. Part of the way that these are handy, I can take this first triangle. I'll take the 30, 60, 90 first. I'm going to copy it and go to a unit circle and paste it. If it lets me. It won't. I think it's too much there, so I'll group it. Now I'll copy it. Now I'll paste it. Really? Not gonna happen. That's a shame. Not a big deal.
Well, that's only the first four.
I can just draw one. This is the 30, 60, 90 tool. And I'm going to draw one from the center. Oh, I see what's happening. I apologize. I want it to be here. There's a 30, 60, 90 right triangle. What's that point? This distance
3, 4.
right here is root 3 over 2. This distance here is 1 over 2.
So that's okay.
So this is the point, root 3 over 2, comma, 1 over 2. That's the coordinate of that point, because this distance here was root 3 over 2, and this distance here was a half. I can do the same thing for 45, 45. I won't take the time to actually draw the proper angle. I can draw a 45 degree angle. So I'll call this one right here. It'll be 45 degrees. If we think about the triangle that it forms, the triangle that it brings down to the ground, to the x-axis, what was this distance here?
2,
What was this distance here?
2.
So this point is root 2 over 2, comma, root 2 over 2. Good. We'll do one more. I can take my 30, 60, 90. Instead of having the 30 degree angle down here, I can have the 60 degree angle up here. So this whole entire angle, 60 degrees, gives me this triangle. What would be the x distance? 1/2. It's this same triangle we had over here, with the 1/2 and the root 3 over 2. Now it's switched. So this is the point 1/2, and this is root 3 over 2. At this point there. It's getting real tight. Those 3 points, root 3 over 2, root 2 over 2, and 1 over 2, are going to appear all over this circle. We've already got a few easy points. You know, this is the point 1, 0. You know, this is the point 0, 1. This is the point negative 1, 0. And this is the point 0, negative 1 down here. But now I can take these reference angles we've talked about. And if this is 30 degrees, then this point here is basically the same as this point here, although it's not graphed correctly. This point here is 30 degrees, is basically the same as the one that comes from this triangle. So what's this coordinate going to be?
So I can put a point for 3 over 2.
The x distance is negative. I'm traveling in a negative direction. So it's negative root 3 over 2, comma. The y distance is still positive. Positive 1/2. And that comes from our references. Okay, stop there.